Limits in calculus help us define and compute derivatives. On the other hand, L'Hopital's rule helps us use derivatives to calculate limits. Now, the very first thing to know about L'Hopital's rule is to know when not to use it. You do not use it in a situation where the function in question is continuous at the number that x is approaching. With that kind of problem, you evaluate the limit just by substitution. I have purposely made the part A of the very first problem to be that way, though in all the other parts we will use L'Hopital's rule. The limit as x goes to 0 of 4x plus 5 over 3x minus 7 can be found by substitution because the only value of x where this function fails to be continuous is when the denominator is 0. That occurs at x equals 7/3, not x equals 0. We evaluate this limit just by substituting x equals 0. We're not dividing by 0. This limit does exist. It equals 5 divided by negative 7, which is the same as negative 5/7. If you had mistakenly used L'Hopital's rule here, you would have gotten an answer of 4/3, and that would have been wrong. The answer is negative 5/7. This is a situation where you do not use L'Hopital's rule. All the other problems you do. What makes them a problem where L'Hopital's rule applies? Part B is the limit as h goes to 0 of sine of 4h divided by 5h. The first hint that this is a situation where L'Hopital's rule might apply is that this function is undefined at h equals 0. You'd be dividing by 0. But that's still not quite enough, because the top also in that case needs to go to 0. Sine of 0 is 0. Sine of 4 times h goes to 0 as h goes to 0. Therefore, this is a situation where we can try to apply L'Hopital's rule to evaluate the limit. This is a 0 over 0 indeterminate, not indeterminate, but indeterminate form. It's a situation where you have a fraction, a quotient, where the top and the bottom are both going to 0. Another kind of indeterminate form is infinity over infinity. That's going to occur with part D right there. We'll get to that. It's in this kind of situation where you can try to apply L'Hopital's rule, though I haven't told you how yet. You should be aware that you might have to apply L'Hopital's rule more than once. Another thing to be aware of is that you might have to use a trick to apply L'Hopital's rule before you can use it. And another thing to be aware of is that sometimes L'Hopital's rule is actually not helpful. In these problems it will be helpful, but what does it say to do? It says that this limit, if it exists, will equal another limit, that is the limit of a new ratio, a new quotient, whose numerator, top, and denominator, bottom, are the derivatives of the original numerator and denominator. This is not the quotient rule. We are not taking the derivative of this entire quotient here, just the top and the bottom individually. The derivative of sine of 4h with respect to the variable, which is h, is 4 cos 4h. That's the chain rule there. And the derivative of 5h with respect to h is just a plain old 5. I did not use the quotient rule there. I took the derivatives of the top and the bottom individually and made a new fraction. If this limit exists, and it does, then this limit will exist and they will be equal. That's the essence of L'Hopital's rule. We'll see intuitively why L'Hopital's rule works at our very last problem, where we'll think about a problem graphically, but right for now we're just trusting it. This limit can be evaluated without L'Hopital's rule. If you try to use L'Hopital's rule, you get the wrong answer. This is a continuous function of h. You can just substitute in h equals 0. So you get 4 times cosine of 4 times 0 is 0, divided by 5. Cosine of 0 is 1, so this becomes 4/5. 4/5 is the correct answer, 0.8 for part B. On to part C. This one looks kind of complicated. The limit as t goes to 0 of this ratio, e to the 2t minus 1 minus 2t all over 3t squared. Once again, check to see, does L'Hopital's rule even apply? Can you try using it? Is it an indeterminate form? Yes, it is. Why? Because both the top and the bottom are going to 0 as t approaches, in this case, 0. 3 times 0 squared is certainly 0. This goes to 0 as well. E to the 0 is 1. 1 minus 1 is 0. Minus 2 times 0 is still 0. This is a 0 over 0. IF is my abbreviation for indeterminate form. Again, say indeterminate, not indeterminate. And that means we can try to apply L'Hopital's rule. we can take the derivative of the top and the bottom individually and try to compute the new limit of the new ratio. The derivative of the top by the chain rule is 2e to the 2t minus 2, and the derivative of the bottom is 6t. But what happened here? This is still an indeterminate form. Both the top and the bottom still go to 0 as t goes to 0. Still a 0 over 0 indeterminate form. So we'd have to try using L'Hopital's rule again. And in general, with certain problems at least, it's not necessarily helpful. You don't necessarily make much progress. But we do here. When we take the derivative of the top and the bottom individually, we get 4e to the 2t and 6. Now we can plug in t equals 0. This is continuous everywhere. We get 4e to the 0 over 6. E to the 0 is 1. 4 over 6 is 2/3. The answer is 2/3. You can confirm these answers, by the way, with a graph. Let's just go ahead and do this one here. Of course, in my calculator, I've got to use the variable x. So I'm going to think about the original function here. E to the 2x power, and then minus 1 minus 2 times x, all divided by, in parentheses, 3x squared. I'm letting x go to 0. So I want to graph this on a window that's close to 0, like -1 to 1 for x. What answer did I get? I got 2/3 for the answer. So let's go y min, y max to be 0 and 1. And let's make the tick marks on the y-axis 1/3 of a unit apart and graph it. There's the graph. You can see it does approaching 2/3. This is 1/3 here, that's 2/3, that's 1. You can see this graph does seem to be approaching 2/3 as t goes to 0. Technically speaking, the graph has a point missing on it because technically speaking, this function is undefined when t is 0. So there would be a hole in the graph, but it's what's called a removable discontinuity. If you redefine the function to equal 2/3 when t is 0, you would get a continuous function. But the point here is to compute the limit. All right, part D. This is a different kind of thing. We're letting x go to infinity now instead of a particular number. We got a rational function of x where both the top and the bottom have the same degree, 2. That means the limit exists, and you actually can figure out this limit without L'Hopital's rule. Maybe you've learned previously that if the degree of the top and the bottom are the same, you look at the ratio of the coefficients at the highest power of x, 3 over 2, 3/2. That actually is going to be the answer. Effectively, intuitively, because this ratio acts like 3x squared over 2x squared when x is large. You can ignore the other terms. But you can also confirm this with L'Hopital's rule, and that's what we want to do. I mean, I did just say in the directions here, calculate these limits, and I already said the answer. But let's go ahead and use L'Hopital's rule. It's not a 0 over 0 indeterminate form. Instead, it's an infinity over infinity indeterminate form. Infinity over infinity if. It doesn't mean infinity is a number. You know, letting x go to infinity just means x gets bigger and bigger without bound forever and ever. That's what you imagine, at least. You can make it real precise without thinking about motion, but that's what we imagine. So infinity is not a number. So when I say infinity over infinity indeterminate form, I'm not implying that infinity is a number. I'm just saying what's the nature of what happens to the top and the bottom. This video is about not just L'Hopital's rule, but also growth and dominance. These functions on the top and the bottom are growing large as x gets large at, you might say, roughly the same rate because they're both quadratic. But more precisely, what does the answer end up being for this limit? It ends up being 3/2. In other words, this function divided by this function is close to 3/2 when x is large. But how do you apply L'Hopital's rule here? You, once again, take the derivative of the top and the bottom individually. The derivative of the top is 6x plus 4. The derivative of the bottom is 4x minus 6. This is still an infinity over infinity indeterminate form. So we once again use L'Hopital's rule and take the derivative of the top and the bottom individually. You get 6/4. That's a constant function equal to 6/4 or 3/2, 1.5. And that is the answer. And that, if you want a little bit of a graphical interpretation, would be the y-coordinate of the horizontal asymptote. The graph, this function is going to approach the line y equals 3/2 as x goes to plus infinity. And actually, this calculation is the exact same as if x goes to minus infinity. And the top and the bottom still go to plus infinity, even if x goes to minus infinity, because of the quadratic being an even power. Nobody typically writes minus infinity over minus infinity in indeterminate form, though, if you had a cubic there and a cubic there, for example. So don't worry about it. You get the same answer. The last part of this problem is to calculate a right-hand limit. The limit as x goes to 0 from the right of x times natural log of x. You've got the product of two things that are kind of conflicting. X is going to 0, but natural log of x as x goes to 0, if you know the graph of natural log of x, goes to minus infinity. The graph of natural log goes to minus infinity. You've got something going to 0 times something getting very, very large negatively. Could this limit possibly exist? This is the limit, as x goes to 0 from the right of x times natural log of x. This is what you would call a 0 times infinity indeterminate form. And I'm not going to bother to write a minus infinity. Just call it 0 times infinity. It's unclear which factor will win out. Will this limit be 0, or will it be minus infinity, or something else? It's not clear. We need L'Hopital's rule, but we have to use a trick first. This is not a fraction. You cannot think you can use L'Hopital's rule by differentiating each factor in a product. That doesn't work. So what do? We use a little trick. We write it as a fraction. One way you could do that, and I think this is probably the best way to go, is to think of multiplying by x as dividing by 1 over x. So this function is also equal to natural log of x divided by 1 over x. And the function was undefined at x equals 0 anyway, right? Natural log of 0 is undefined. We're only thinking about positive values of x. This definitely is true. These two functions here and here are the exact same function. But now it's no longer a 0 times infinity indeterminate form. It's now an infinity over infinity indeterminate form. Both the top and the bottom of this fraction go to infinity as x goes to 0 from the right. This goes to plus infinity. This goes to minus infinity. Don't worry about putting minus signs anywhere. This is an indeterminate form. So we can apply L'Hopital's rule. Doesn't matter that it's just a right-hand limit. The derivative of natural log of x is 1 over x. The derivative of 1 over x is negative 1 over x squared. Check it, double check that. Now this is still, technically speaking, an indeterminate form. The top's going to infinity as x goes to 0. The bottom's going to minus infinity as x goes to 0. However, we don't need to use L'Hopital's rule again, and this is something you should look for. Instead, we can simplify this fraction. The top is x to the negative 1. The bottom is negative x to the negative 2. We could subtract those exponents. Negative 1 minus negative 2 is plus 1. The negative sign can come out in front. So this is really the same as the function negative x. Another way to see that, instead of subtracting the exponents, is to multiply the top and the bottom of this by x squared. The x squared completely cancels on the bottom. You get partial cancellation on the top, and you're left with a negative x. And this limit definitely is 0. It exists. Same as this limit by L'Hopital's rule. Same as this limit because these two functions, again, are equal for positive values of x. Okay? And these two functions are equal too for positive values of x. So everything is fine here. Problem 2 is about dominance of one function over another. Two parts of the problem. Part A, use a limit to confirm that the square root of x dominates natural log of x as x goes to plus infinity, as x gets bigger and bigger without bound. How do you do that? What does that even mean? It means the square root of x ultimately grows a lot faster than the natural log of x as x gets bigger and bigger. That's what it means. If you graph both of them, let's go ahead and do that, you will see ultimately the graph of the square root of x growing a lot faster than the graph of natural log of x in the end. Let's pick a window, say 0 to 10, and see what we see. First function, square root of x. Second function is natural log of x. It looks like they're growing perhaps at about the same rate. Not enough to call it dominance, you would think. Well, what happens if you make the window bigger? It's not just that square root of x grows faster than the natural log of x. It's in the end that it grows a lot faster. If I go to 100, or maybe even 1,000, and maybe we would need to go to, say, 50 here. Let's see what we see. There's the square root function. And the natural log function, okay, you can see the growth rate is not close together. Square root of x is growing a lot faster. But how do you prove this with the limit calculation? You compute the limit as x goes to plus infinity of a ratio, and you show the ratio is 0. If square root of x is dominating natural log of x, you'd want to put the natural log of x on the top and the square root of x on the bottom. You want to show this limit is 0, and that's enough to confirm, essentially by definition, that this function dominates this function as x goes to plus infinity. But this is an infinity over infinity indeterminate form, so we need L'Hopital's rule. Take the derivative of natural log of x, get 1 over x. Take the derivative of square root of x. Square root of x is the same as x to the 1/2 power. So we would get 1/2 x to the negative 1/2 power. This is also the same as x to the negative 1. Subtract exponents. Dividing by 1/2 is the same as multiplying by 2. You could say this is the same as the limit as x goes to infinity of 2 times negative 1 minus negative 1/2 is negative 1 plus 1/2, which is negative 1/2. And that's the same as the limit as x goes to infinity of 2 over the square root of x. Now this is no longer an indeterminate form. You could call it 2 over infinity, but that doesn't count as an indeterminate form. So far we've only seen 0 over 0, infinity over infinity, and 0 times infinity. This is 2 over infinity, which is not indeterminate. Don't try to apply L'Hopital's rule, although I think if you did it, you'd probably get the right answer. Well, don't think about doing it that way. This definitely goes to 0 as x goes to infinity. It's not continuous at infinity because infinity is not a number, but it definitely gets smaller and smaller, arbitrarily close to 0 as x gets larger and larger. You can plug in numbers and make it get as small as you like. So this limit is 0, and that means this limit is 0 by L'Hopital's rule, and that means that square root of x dominates natural log of x as x goes to infinity. The bottom goes to infinity much faster than the top does, enough to make this limit 0. We do something similar in part B. Use a limit to confirm that e to the 0.1x dominates 100x squared as x goes to infinity. So we've got to do a similar kind of limit calculation with e to the 0.1x in the bottom and 100x squared in the top. We're wanting to show this goes to 0. That would be enough to show the exponential growth function dominates the polynomial growth function, as you should already know intuitively. This is an infinity over infinity indeterminate form. We can apply L'Hopital's rule. Take the derivative of the top and get 200x. Take the derivative of the bottom and get 0.1 e to the 0.1x. Still infinity over infinity. So we take another limit. We apply L'Hopital's rule again. Get 200 on the top, and 0.1 squared is going to be 0.01 e to the 0.1x on the bottom. And this is similar to what happened in this problem. Now we've got a constant, 200 in this case, divided by something going to infinity. This is no longer an indeterminate form. This is going to go to 0 as x goes to infinity. This limit exists and it is 0. It's no proof, but it's intuitive. And by L'Hopital's rule, that means this limit is 0 as well. And that's enough to say that the bottom function dominates the top function. This limit goes to 0, so the bottom goes to infinity a lot faster than the top does. Problem 3 involves new kinds of indeterminate forms. In part A, we're looking at this limit. The limit as x goes to infinity of 1 plus x to the 1 over x power. You've got something in the parentheses here getting very, very large to a power that's getting very, very small. Now you know that any number to the 0 power is 1, except technically 0 to the 0 power, which is undefined. In fact, 0 to the 0 is an indeterminate form. So since the exponent is getting closer and closer to 0, you would think maybe, in spite of the fact that this is getting bigger and bigger, that this approaches 1 in the end. And that might be the answer, but it's not completely obvious. We do need to try to confirm it using a logarithm and L'Hopital's rule. How in the world are we going to use a logarithm? Okay, here's the idea. Let's let y equal the function we're considering here, 1 plus x to the 1 over x power. That is a function of x. I could call it f of x if I like. Take the natural log of both sides of that equation. And then, here's the key, use a property of logarithms, in this case the property that the power there can come out in front, like this. And you can then write this actually as just one fraction, natural log of 1 plus x over x. And that looks like something maybe we can apply L'Hopital's rule to, and that's what you do. Get an answer if the limit exists. Just pretend, for sake of argument, the limit is 7. That's not the answer, but if it were 7, then natural log of y would be approaching 7 as x goes to infinity. And that would mean y itself is approaching e to the 7 power. Does that make sense? Because natural log of e to the 7 is 7. Really using some continuity there, but we'll be fine with an intuitive understanding. So the limit, as x goes to infinity, of the natural log of y, keeping in mind that y is a function of x, is the same as the limit as x goes to infinity of this thing, because that is the natural log of y. And that is an infinity over infinity indeterminate form. We can use L'Hopital's rule to try to evaluate it. Take the derivative of natural log of 1 plus x and get 1 over 1 plus x. The derivative of x is 1. And yeah, this simplifies to 1 over 1 plus x. And as x gets large, arbitrarily so, it definitely goes to 0 as x goes to infinity. So the natural log of y is approaching 0 as x goes to infinity. Therefore, the limit as x goes to infinity of y itself, 1 plus x to the 1 over x, must be e to the 0, which is 1. The answer is actually 1 in this case, but that wasn't a guarantee without actually going through the calculation. Part B is similar. Use a logarithm and L'Hopital's rule to find this limit. A and B are constants. A and B are constants. Will we get 0 again or 1 again? Not clear. Is it a new kind of indeterminate form? Yeah, it is. This one right here was a infinity to the 0 indeterminate form. For this one, the function is y equals 1 plus a over x to the b times x. As x goes to infinity, this thing in the parentheses is going to 1, and this thing, the power, is going to infinity. This is a 1 to infinity indeterminate form. So maybe the same trick works. Take the natural log of both sides. Natural log of 1 plus a over x to the bx power. Use a property of logarithms to bring the b times x out in front. And as x goes to infinity, this now becomes an infinity times 0 indeterminate form. Natural log of 1 is 0. A over x is going to 0 as x goes to infinity. But if we want to apply L'Hopital's rule, we need to write it as a fraction. Maybe the same kind of trick as a previous problem will work. We could write this function as b times natural log of 1 plus a over x, all divided by 1 over x. I think it might be helpful to go ahead and write 1 plus a over x as getting a common denominator of x, x plus a over x, and then use another property of logarithms to write this as b times natural log of x plus a minus b times natural log of x. That'll make taking derivatives easier. And the bottom is x to the negative 1 power. Ignore that mark there. What now is the limit as x goes to infinity of the natural log of y, which would be the limit as x goes to infinity of this entire thing here. This is now a fraction that could be thought of as x gets large as a 0 over 0 indeterminate form. Now, technically speaking, I haven't really proved that the top goes to 0 as x gets large, but it should be intuitive. Natural log of x plus a minus natural log of x as x gets really large, and a is fixed. The a doesn't really matter much. You've got essentially two things that are close together. The natural log function does grow, but it grows slower and slower. It's concave down. That's enough, it turns out, to verify that this top goes to 0 as x goes to infinity. Again, that's no proof. So I'm going to go ahead and call it a 0 over 0 indeterminate form and use L'Hopital's rule. Take the derivative of the top, get b over x plus a minus b over x. Take the derivative of the bottom, get negative 1 x to the negative 2. I'll write that as negative 1 over x squared. Should I apply L'Hopital's rule again? Doesn't sound like a good idea. It doesn't look like a good idea. I'm going to multiply the top and the bottom by the least common denominator here of everything, x squared, and also an x plus a. If I do it to the top, I got to do it to the bottom to compensate. Just a little trickery here. And how does this simplify? The x plus a cancels with that x plus a, leaving a b times x squared. And here with a minus b over x times this, one of the x's cancels, leaving you with a minus bx times x plus a. And the bottom, you have the negative sign here. The x squareds cancel. You're left with negative in parentheses x plus a. This part right here is the same as negative bx squared minus abx. And the minus bx squared cancels with this bx squared. So in the end, we get the limit as x goes to infinity of the negative abx over, I'll distribute the minus sign through there, negative a x minus a. We could use L'Hopital's rule again. We don't have to. This is a rational function where the degree of the top and the bottom are the same. But I'll go ahead and use L'Hopital's rule again. This is an infinity over infinity indeterminate form. Take the derivative of the top and the bottom individually, get negative a over b over negative 1. The negative signs cancel, leaving you with an answer of a times b. That's not the final answer, though. That's the limit as x goes to infinity of the natural log of the function we're interested in. So to find the limit of the function we're interested in, limit as x goes to infinity of y itself is the limit as x goes to infinity of the original function was 1 plus a over x to the b times x power. This turns out to be e to the a times b. Okay? And this is related to compound interest if you want to look into it deeper. And number 4, we've got the difference of two functions that are both, in this case, going to infinity as x goes to 0. This is an infinity minus infinity indeterminate form. How could we possibly use the L'Hopital's rule for this? We always apply L'Hopital's rule in the end to fractions. So I've got two fractions here. Maybe I should combine them into one fraction by getting a common denominator of x times e to the x minus 1. In the top, then, we'll have to multiply the top and the bottom of the first fraction by e to the x minus 1. So we'll get e to the x minus 1. And for the second fraction, we'll have to multiply the top and the bottom by x, minus x. Let's go ahead and expand out the bottom. So we have e to the x minus 1 minus x divided by x e to the x minus x. As x goes to 0, the bottom's definitely going to 0. Is the top going to 0? Yes, it is, because e to the 0 is 1. 1 minus 1 is 0. Minus 0 is still 0. This is now a 0 over 0 indeterminate form. So we used a little trickery again to convert it to a fraction and help us now evaluate the limit. We now apply L'Hopital's rule, take the derivative of the top and get e to the x minus 1. Take the derivative of the bottom with the product rule there, get 1 times e to the x. That's the derivative of x, the first function, times the second function, e to the x, plus x times the derivative of the second, x e to the x. The derivative of minus x is minus 1. This is still an indeterminate form. Plug in 0. The top is 0. The bottom is 0, because e to the 0 is 1. This is still a 0 over 0 indeterminate form. Let's try L'Hopital's rule again. It's possible that maybe we'll never stop, and so it's not helpful, but let's see what happens. Take the derivative of the top and the derivative of the bottom, using the quotient, the product rule again here. The derivative of minus 1 is 0. So this, the limit as x goes to 0 of e to the x over 2 e to the x plus x e to the x. If you plug in x equals 0 now, you do not divide by 0. Both the top and the bottom are defined, and in fact non-zero when x is 0. This is continuous at 0. We get e to the 0 over 2e to the 0 plus 0. E to the 0 is 1. This becomes 1/2 for the answer. And yeah, that is the answer for this limit. Number 5 is our promised graphical problem. We've got two functions, f and g, given with these graphs. This increasing in concave down function for f and decreasing in concave up function for g. And we also see their tangent lines at the point 4, 0. They're shown in the figure below. Find the limit as x goes to 4 of f of x divided by g of x. Intuitively, if we use the tangent lines to approximate both f and g, we could say, you can see that they're close together. F of x is close to its tangent line, 1.4 times x minus 4. And g of x is close to its tangent line, negative 0.7 times x minus 4, when x is close to 4. You can see this dashed line is close to this function, and this dashed line is close to this function when x is close to 4. But that simplifies very nicely to 1.4 divided by negative 0.7, which is negative 2 when x is close to 4. The ratio of these two functions is close to negative 2. That is the answer. But did we really apply L'Hopital's rule there? Not really. And even so right now, well, okay, I will apply L'Hopital's rule here. This is a 0 over 0 indeterminate form because you can see graphically both the f function and the g function are approaching 0 as x approaches 4. But we also need to assume in what I'm about to show you that these derivatives, f prime of x and g prime of x, have limiting values. It's intuitive from the picture that they do because you have a slope that's well defined to the tangent line in both cases. But you'd want to really prove that rigorously to know we can say this. In the end, this is going to be a continuous function of x at x equals 4, and the slope at 4 is given by the slope of the tangent lines. So we get f prime of 4 divided by g prime of 4 in the end. F prime of 4 is the slope of the tangent line, which is 1.4. G prime of 4 is the slope of this tangent line, which is negative 0.7. So in the end, we still get negative 2, and that would be how to use L'Hopital's rule to solve that problem. Thanks for watching.